Hello and welcome back. I'm excited to introduce you to one of our closest consulting partners, SimWell Consulting. Please welcome Pierre Bedard, Nomesi Kokotse, and Denise Matarangas. So thank you everybody for joining, and we're excited to see your presentation.
Thank you, Max.
Thank you.
Thank you.
Yeah, thanks.
So everybody see the presentation? Yeah. All right. I will go anyway. So welcome to this presentation about high-frequency public transit in Quebec City. My name is Pierre-Olivier, and I work at the RTC. I'm accompanied by my colleague Nomesi and Denis from SimWell. So let's start by presenting the Réseau Transport de la Capitale. We'll refer to it as RTC for the rest of this presentation. We are a public transit agency ensuring the mobility of people in the urban agglomeration of Quebec City. A couple of quick facts for you guys. This year marks the 50th anniversary of the organization. We usually do more than 4,000 trips per day with our 600 vehicles. We have a little bit less than 2,000 employees. Before COVID, we had about 85,000 riders per day. 60% of these riders are on the high-frequency routes, where maintaining the bus spacing and the service quality is a big challenge. So we realized that a simulation model would be a great tool, so we turned to SimWell.
So at SimWell, our mission is to be one of the world's best team dedicated to simulation. We have a diverse team of simulation, AI, and software engineers building a world-class solution for our client like RTC. We're based in Canada, in the USA, with a global team of engineers building model around the clock. So RTC came to SimWell to build a simulation model. They had already built a great global vision of their project with detailed specifications and a quality approach centered around involving stakeholders. So that was a very exciting project for us to jump in. And this project was built out of three main guiding principles. So the first one was building onto what has previously been done. So they've done a lot of work with the project, even starting to model. In fact, the model was a component of a bigger project built around Six Sigma concepts. For example, many focus group has been held with drivers, managers, schedulers, and a lot of great ideas came out of these, and other not so great. So this is where the model will come into play to test the ideas that came out from these activities, ideas to solve the problem they are facing. Autonomy was also a really important principle we wanted to improve. So having a model in which RTC team can play with the switches and levers with an easy-to-use interface without having to rely on consultants to run many scenarios, even some they didn't think about in the first place in the design phase. Was really important. So the idea was to give them a fishing rod instead of the fishes. So having the model, the most data-driven possible was a constant driver into the design sessions. The entire project, including the model, was built with change management and stakeholders in mind. This is an image representing the allegory of the cave, an analogy that comes from Plato. If you remember your college philosophy classes, essentially, you can have the best solution in the world to a problem. In this case, that will be the sun. If it will change people's habits and take them out of their reality, and their reality in this case is being in a cave with only seeing the shadows. So if you want to take them out and show them the suns, you have to do that gradually. If not, they'll be dazzled by the sun, and they just want to go back to the cave, to the shadow where it looks more familiar to them. So a simulation model in this case is the transition line. We want to use that to bring our people from an initial state to an improved one, but not without being dazzled. So based on these principles, we address a classic business problem faced by all transit agencies in the world offering high-frequency services, bus bunching. But Pierre-Olivier, what is bus bunching?
Yeah, without further ado, let's dive in the problem we're trying to solve. So, in a perfect world, every bus would get to a stop at the planned headway to efficiently service the customer. This usually means that every bus is loaded evenly. But let's say, for example, that the first bus on the left gets stuck behind traffic. That means more people waiting at the next stop than expected. So it takes more time to service each stop. Meanwhile, the next bus has fewer people getting on and can easily catch up with the first one and create bus bunching when two or more buses arrive at the same place at the same time. You can also see that the load is not the same between each buses. The first one is loaded and the second one is near empty, having an effect on comfort. But this creates the real problem for our customers, the service gaps, when there's no service at the stop for a long period of time. Also, this has the potential to spread to the rest of the line because behind the service gap, there's more people at the stop, more people in the bus, more people at each stop, and the next bus can catch up. This creates bus bunching and the service gap. So those gaps make taking the bus unpredictable and frustrating. So the real question becomes how to prevent or break this cycle. Combating bus bunching is critical to ensure frequent service actually run frequently. And more transit agencies are trying to address the problem. As you can see, there's news from New York, Chicago, and Boston, and other major cities trying to solve their problem. So the objective of this project is to improve the service quality for the customers while maintaining or improving the quality of work for bus drivers. So these are the two pillars on which the RTC operates. Going back to change management, operation controllers, their decisions are based on their experience and intuition. So the decision criteria is different. It would benefit from being more consistent. So one way the model helps is to demonstrate new ways to operate and find the most beneficial solutions. Also, some methods are not popular with the upper management or have an impact on planning and infrastructure. So with the model, we can test the solutions and see the potential impact and risk for the customers and bus drivers before going in the real world. So as Denny said, we had workshops with all the stakeholders to identify the potential solutions. We had more than 72 solutions that were identified. And a lot of solutions can be implemented to reduce bus bunching. But the time horizon before implementation can vary depending on the solution. So the city is a major contributor by implementing bus-only lanes and transit signal priority, for example. Once that is done, it is the role of the transit agency to ensure reliable service to the customers. Planners and schedulers usually have their shot at least 4 months before the operation on the field with the schedule, choosing the different headways, or deciding if we go with all-door boarding, which reduces the time at each stops. After that, in real time, the operation controllers have the last chance to correct the problem by taking measures like overtaking, injecting a bus, passengers transfer, etc. So all of this, just to say that the model focus on the shorter term corrective actions, and the more long-term decisions are modeled by changing the input data. Then there was other workshops conducted with smaller groups to define the functional and the technical specifications of the simulation model. And now I pass the floor to my colleague Nomesi to talk about the data this group had to work with.
Thank you, Pierre-Olivier and Danny here. So now we're going to talk about the data part, which is one of the important part of the whole project. So first of all, there is something important to mention here. When we talk about bus means we have a lot of information systems, for example, GPS to track the position, the real-time position. And also at each stop, you have what we call automatic passengers counter, APC. And the APC will help, for example, to know how many passengers board and how many passengers alight at the stop here. Next, please. So when based on all this information, we are able to collect a lot of data, and all this data, for example, on this slide, you can see some of them. You have the information regarding the trip, for example, how many trips per day for each line, the origin destination. When you talk about the bus, which will follow the line, which is line, the bus, you have, for example, the capacity, the travel time. That means the total travel time from the origin to the final destination, or the running time for each pair of stops also. The break time at the end of each trip. That means when a driver drives a bus from the beginning to the end, there's for example, a few minutes of break time before they decide to go to the next trip here. The arrival time at each stop, and also departure time. So all this information help us, for example, to reproduce exactly what the bus is able to do or the bus did from one stop to another. At the third position, you can see some characteristics regarding the stop and also the passengers here. Sorry, thanks.
Sorry about
No,
that.
it's okay. Yeah, you can go further, please. Thanks. When you talk about data, there's something important to know, or I'm quite sure that everybody will know what about that here. You talk about variability. That means, for example, when a bus is traveling, you have the traffic, you have the traffic lights, you have, for example, season. Winter is quite different from summer, or sometimes you can have more passengers than usual at the stop. And all this information will affect, or will have an impact on the data. So you're going to have a kind of variability. So we catch up all these different sorts of variability inside of historical data here. So Dennis.
So with the problem defined, a lot of interesting solution, and all this great data available, it's time to tackle the variability using that cause bus bunching using a simulation model. So here's the solution infrastructure, pretty simple. The model is fed by historical data extracted from RTC data warehouse. This makes it possible to calibrate the different function of the model, such as travel times, driver behaviors, customer boarding times, ridership at the various stops, and all the other one that Nomesi mentioned. And from the RTC planning software, we extract the schedule we want to test. For example, if we want to reduce or increase the frequencies or schedule run times, what would be the effect on quality and cost is something we can do pretty easy. And then the simulation model gives metrics, visualization, information for optimal decision and appropriate change management. Whether it's to adjust the schedule, build preventive or corrective action policies for the control center, or to give the board decision brief about strategic or tactical decisions, such as determining service levels, changing operating modes, outdoor boarding, or any other important changes to the process. The model is there to support them. And then RTC is ready to operate in their real-world service with improved schedules, efficient policies, and to complete the loop, data is refreshed and adjustment can be made if there is significant changes in the transit system, like say a pandemic. So why we choose AnyLogic based on the guiding principles I mentioned earlier, specifically for flexibility and change management. Of course, one of the main purpose or goal of using a simulation model for the RTC team experts was to figure out which could be the best solution to combat or to fight their bus bunching problem. But a very big part of it, it's also to allow stakeholders, among them managers, drivers, operation controllers, to witness experimentation and understand how some solution can really help them, not just with tables and statistics, but with their eyes. For example, we reproduce on AnyLogic an identical view of the control center automatic vehicle locator system. So they feel like in their own environment, and they can understand when we show some strategies or some policies to apply, they can relate to that very easily. So the UI and animation was very important, and AnyLogic was the best tool with its great graphical interface, possibility of showing multiple views and strong GIS features. And of course, you probably all know probably all know AnyLogic legendary flexibility with Java coding, and also the ability to package a model as a standalone Java application was also a big plus for RTC, who didn't want to buy a license yet for now, but still being able to play with the model. So, Nomesi, how does the model works?
Yeah, thank you, Dennis. Yeah, so we're going to talk now about how the model works here. For the model, we collect the data for 2008 and 19. That means before the pandemic as reference scenario. That means we clean, we infer, we made a lot of things, and we have finally distribution for all variables. Yeah, and all these values will help will help us as an impact for the model. Yeah, next please. And I'm going to give you some examples exactly about how the model works here. For example, at each stop, what the bus did exactly. The bus arrived at the stop, opened the door, alight people, board people. So all this time, we catch this time in historical data or based on historical data. And also there is something important. For example, after alighting and boarding passengers, sometimes you have a traffic light which is red, and that means more time for the bus at the stop before the bus moves. So we can reproduce exactly all this process. Next, please. There's something also I would like to show on this slide is when you talk about a stop, a bus stop, you have, for example, at a specific time, you can have 10 passengers who board, yeah. But there is something we need to define is what we call passengers arrival rates. That means around 7 minutes before the bus arrives, you have 2 passengers, and at the end, when the bus arrives, you have 10 passengers. So you can see on this curve or on this graph what we call the arrival rate for the passengers here. There's another example about how the model works here, and we talk here about we show here what we call destination probability. That means when somebody board on a stop, what will be the stop where the person will alight here, based on the principle of probability, and we use the historical data and we build a kind of table which help us. You can see on this slide, for example, 4 person board, and based on the probability, 1 will alight at the next stop and 3 will alight at the next stop here. Please, next. Another example for regarding how the model works. Here we try to summarize what we call the running time. It was a real challenge to represent the running time. That means we know the total time, but for each pair of stops, how the bus will move from one pair of stop to another, it's something really tricky. So we use an innovative approach which is Markov chains. That means from one pair of stop to another, we're gonna choose or we're gonna make a kind of random choice based on a principle of Markov chain. That means the next step will depend on the previous state. So it's not a time which is not really current here. So Pierre-Olivier, can you talk to us about some KPI?
Yeah, absolutely. So the RTC had no existing KPI to represent the real operational situation in a high-frequency environment. This is because we are used to operate using schedules, and we are trying to manage an headway with this project. The first 2 indicators can be used to compare real-life data, and the last one, passengers' comfort level, can only be calculated in a simulation environment because the passenger is an agent. So this is a bonus of the simulation model. Also, because the application we have is a standalone application, we had the need to have an add-on module to run a large number of experiments. For example, we have 8 corrective actions we can model directly in the application, each with a different set of parameters, calibration we can use. So the number of experiments we can grow exponentially each time we want to test a different set of parameters. So if we want to test just 2 states, like on and off, we have about 256 combinations. If we want to test 3 states, we have 6,000. If we want to test 4 states, we have more than 65,000. And that is only for one set of input data. So that is really useful for the practitioner. And now we're gonna go to the model demonstration. So the interface is in French, sorry about that. You have to bear with me with this one. So, go like that. So we start by opening the application and we see the beautiful Château Frontenac. From there, we have different options to set up an experience. So we can choose if we use the schedule mode or the headway management, the type of regulation that will be allowed, and the parameters for each. The model has preloaded tables. So if you want to make change to the input data, you need to check one of the boxes right there. Those are all the input tables we can change. If we do not select the fluidity level, the model would give a random seed to determine it, but we can choose to lock in one of the states for the time between each stop. And finally, we choose what the data we want to extract in text file. So the purpose of this visual interface is to be able to communicate efficiently. So we have 3 different views. We have the map, the control view, and also a statistic view, real-time statistics. So you can also increase the speed of the simulation if you want to. So towards the end of the morning rush hour, we will see there's already trains and gaps forming right there. And you have different statistics also regarding the load of the bus and the spacing. So with the map view, you will start to see also corrective actions in real time. There's a legend on the left. You see the bus stopping and servicing each stop. So right there, you see there's a bus lighting only. So we're trying to get quickly from the bus behind him. You can also replace on schedule. So it does not service the end of the line and to start on time the next stop. And also there's bus injections. So those 2 buses have near empty buses in front of them that were injected. And then we go to the experiment plan add-on. You will see what it is like to see the application backside if you want. So you open an Excel that's another input table and you can put the different combinations you want in there. And then basically you have the, you can choose the number of replications you want in this interface, change the input data also, and then you press play basically. There's no animation with this one as it's really just to run a batch of simulations, but you get output data that help you to analyze the data further with your indicators. So, to you, Dennis.
Yeah, thank you, Pierre-Olivier. Now RTC have a simulation model. They're playing with it. They're in the stage of assessing different solutions and a lot of combination of these. And we're currently looking for future phases already. That could include a serious gaming module to train operation controllers. So when a new operation controller comes in, you can try and try to apply the policies that were optimized for the system. And the other step will be an optimization of next day's frequencies and schedules based on resource availability and runtimes prediction. And beyond that, a digital twin could be used to trigger action suggestion for drivers and the control center for preventive or correcting action. And we can add to that cherry on the cake, producing a forecast to have the next day planning mentioned in Model 3.0. This really will be the dream machine for RTC. So this is where we are now, and I'm very looking forward to work with RTC to make this dream machine comes true one day. So thank you, Pierre-Olivier and Messi, for your confidence in SimWell, and thank you, you all, for your attention. And if you have a question, we're ready to answer them.
This one for you.
There's a question.
How can we connect for bus batching in Africa? Like I figure that someone is interested to know more about it, right?
Yeah, I think so.
So yeah, I'll write to you after, and you can contact me directly. But I'll write to you. Yeah, thank you.
Mm-hmm. You have the email somewhere here.
So how did you model traffic? You want to go with it,
Yeah, I can answer to this question. In fact, we do not model the traffic here. The traffic is included automatically in the, how can I say, in the historical running time data. For example, for one day, there's a lot of traffic. So for one stop to another, the bus will take maybe 1 minute. And for another day, the bus will take on the same segment, maybe maybe 2 or 3 minutes. So that means we have more traffic. So this is how the traffic is taken into consideration, but we do not model the traffic explicitly, as you can see it in another, for example, some other model, transportation model. Yeah.
Yeah, basically what the Nomesi was explaining with the markup chain also is that we split like the historical travel time in 10 categories. And like the worst one is the one with the most traffic, and the more fluid one has like no traffic. So that's with the historical data, that's how we model traffic and like many other stuff also. But with the states in the markup chain, we allow these 10 categories to move. So if during the day it starts really bad and then it goes better, there's a probability that it gets better, or it can get worse also. And the dynamic is really within the markup chain.
Is there any papers about this model?
Denny, can you answer?
Soon to be, not yet, because before publishing any paper, we wanted to see more results from the analysis that RTC is currently having. So, but soon to be published for sure. It's a really nice tool for us and RTC, obviously, and we will do that for sure.
Well.
How long would it take to create a new bus line and assess impact on the existing flow?
Create.
I think if like every transit agency and every city has its own particularities. But if we want to create a new line inside the model that is built for a transit agency, that will be pretty quick. Just changing a little bit of structure and the GIS, the line on the GIS. So it will be pretty quick. But having to build a model for all the particularities for a transit agency, since they don't have the same onboard system like a GPS system or automatic passenger counter, needs to be some adjustment there. But
Yeah, maybe I would like to add something is, yes, create a new line, as Denis mentioned already, it is possible. But for example, if it's a new line, if you do not have historical data to simulate how the bus will move, it can be a problem. So it's possible, for example, to make some hypotheses and finally to have a new line with some data, and then you try and see the impact on the previous, I can say the previous lane. Yeah.
How long did it take you to get from model 1 to 3? It's not done yet.
Not yet.
So far we've done model 1. So this is the simulation model we just presented. And how long will it get us to get to model 3? We will find out soon. We're currently talking about that. So so more to come in a couple of weeks.
Yes, thank you so much, RTC and SimWell. You've made everybody think today, so thank you for a great presentation. And everybody, please, if you have more questions, please go into their bios and send it to RTC's emails and SimWell's emails. We will be back shortly. Thanks.